Good afternoon, everybody. Welcome to this session, our fourth in the series of our webinars. This afternoon we will be talking about thermal infrared imaging of crystalline PV modules. It's a very topical subject today, and I'm sure a lot of people have looked at thermal images of modules and have contemplated getting a thermal camera and would like to know what is going on, what can you see. Let me introduce our speaker this afternoon. Our speaker is Mr. Monphias Vumbugwa. He's originally from Zimbabwe. He's a PhD student in the department, and he's done a lot of work on thermal infrared imaging. So over to Monphias.
Hi, can you unmute, please?
Looks like our speaker is muted. We will just try and get hold of him to unmute.
Okay, can you hear me now?
Yes, thank you.
Okay, thank you. Like Dr. Foster has said, my name is Monphias Vumbugwa, and I'm going to be sharing with you the findings of this study, thermal infrared imaging of crystalline PV modules under dynamic operational conditions. Okay. So in this presentation, I'll give an introduction touching on the installed PV modules in the field, mismatch in solar cells, shading on PV modules, and testing methods that are commonly applied on PV modules to check the quality of the modules. Okay, I also show slides when thermal infrared imaging was conducted under dynamic operational conditions, that is under changing soiling conditions, varying load, and under different irradiance and output power. Then I will give the conclusions. Okay, I think you can see my my slides, right? Okay, like I said, then I will give the conclusions. Okay, PV modules installed in the field generate electrical power under dynamic operational conditions, which can result in cell current limiting anomalies that cause underperformance and safety issues on PV modules. So it is necessary to carry out maintenance on PV modules for early detection of anomalies and for the PV modules to operate as expected and have the expected lifespan, and also so that you can have a quick return on investment. So the testing methods that are applied on PV modules in the field include visual inspection, power measurements, TIR imaging, and electroluminescence imaging. Okay, for now I've just stated the testing techniques, but in one of the slides that follows, I will explain more about these testing techniques. So when PV modules are operating in the field, they are exposed to different harsh conditions like sunny, cloudy, change in temperature, shading, which include shade due to trees, buildings, pores, and soiling caused by bed droppings and wind-blown dust. So the dynamics in operational conditions can cause current mismatch in cells of operating PV modules. Okay, this slide is showing a diagram that is indicating current mismatch in series connected cells. So the desired power output produced by a module and delivered to the load is achieved by connecting cells in series in a module. The series connected cells are ideally meant to produce equal currents so that they match in their operating power. But when operating under dynamic conditions, the cells can mismatch. This diagram is showing a mismatched cell due to shading. The shaded cell is receiving less irradiance and it produces less current than the other cells in the substring. This forces the shaded cell to operate in reverse bias and consume the electrical power generated by good operating cells and dissipate the energy as heat, such that it operates at elevated temperature than other cells. This causes non-uniform temperature distribution in the module, which can be detected on TIR images. Okay, shading on PV cells is caused by any contaminants on the front cell of the PV module. So this picture is showing uniform shading due to soiling, while this one is showing that clouds can shade some modules in a string. And uniform shading reduce solar radiation falling on PV cells and affect power output as seen in the next slide. Okay, so let me just finish with the uniform shading, and then I will move on to uneven shading. So as seen on this IV curve, the dark blue one, there is a drop in ISC due to uniform shading That is when comparing to this reference IV curve, the light blue one. So uneven shading can be caused by trees, as seen in this picture, and also bed droppings and soiling on bottom rows of the modules, as seen in these pictures. And uneven shading actually causes bumps in IV curves of the modules, as shown in this IV curve, that is the red one. And it's actually indicating that the shaded substrings have got their bypass diodes, which are across them being activated due to mismatch. So again, when soiling is uniformly shading the bottom rows of cells in a module, they also cause a drop in ISC, and their IV curve does not show any bump because those shaded substrings will be producing equal currents, so there will be no current mismatch. Okay, this slide is showing effects of uneven shading on PV modules. This one is showing shading due to neighboring modules, which partially shaded bottom row and caused the cells to be abnormally hot. These hot cells, due to partial shading, due to grass, and these ones due to bed droppings, as can be seen in this image, and also these small hotspots are due to grass cuttings. So partial shading has to be significant enough to cause current mismatch and hot cells. Otherwise, some shading can just cause hot spots due to different emissivity of glass and contaminants, as shown by these pictures of bed droppings and grass cuttings. Okay, abnormal thermal signatures cause glass cracks, as seen in this picture. Actually, module glass cracks cause scattering of solar radiation falling on PV cells and affect performance. The cracks also interrupt with cell fingers and bus bars, and again affect performance. Discoloration of the encapsulant cause mismatch and impact on performance, since it affects the irradiance that will be falling on the PV cells. This picture shows bent marks on the back sheet, that is indicating damaged back sheet. This creates openings for moisture ingress, which can further degrade the module. And these two pictures show damaged junction boxes, which were caused by abnormal heating in the junction boxes. Hot junction box can be caused by loose connections in the junction box and faulty bypass diodes, which can be as a result of continual conduction of bypass diodes, and also lightning can also cause the bypass diode to be damaged. Okay, in this slide, I will explain the risk of fire due to hot spots or hot cells. This TIR image is showing abnormally hot cells, which can be seen on the TIR image. But interestingly, we can see that the substring in the middle is warmer than the other substring, indicating that this substring has been bypassed by the bypass diode across it, probably because of the broken bus bars in this hot cell. So this substring is not contributing to string power, and the resistive heating in this cell is heating up the cell, and if the bypass diode across this substring is faulty, that is when it is open, when it is open, that is maybe by continual conduction of string power, then the high string electrical power will be forced to flow through this substring and through this defective cell, and forcing the cell to be at a very high temperature, which can cause fire. Okay, other researchers like Claudia Buop, she's an engineer in Germany, showed in their work that smoldering fire can be caused by hot cells. And also these guys also have a research which showed that a cell can operate at more than 300 degrees Celsius if no bypass diodes are used, and this high temperature can obviously cause fire in PV modules. Okay, the testing methods that are commonly applied to test PV modules are visual inspection, IV measurements, EL imaging, and TIR imaging. Visual inspection is a quick method to identify anomalies on PV modules, but other anomalies can be not be detected visually, so they require other testing techniques like IV measurements, EL imaging, and TIR imaging. So if the IV parameters of the measured and the expected IV parameters does not match, then it means the module that will be under test will be having some problems. So as can be seen here, we see the deviation in MPP, which shows that the module under test is underperforming. But to identify the individual cells that cause the module to underperform requires EL imaging and also TIR imaging, as can be seen here. on the EL image showing dark cells, and those dark cells correspond to the hot cell on the TIR image. Okay, for more information on the testing methods, you can search for this report, and also for more information on TIR image, you can also search the work that was done by Claudia Buop. She covered a lot of work on TIR imaging. Okay, so like I said, IV measurements and EL imaging, some of the testing techniques that are applied on PV modules. But these testing methods consume time and they are costly when applied on larger PV plants, since they involve switching off the strings to be tested and disconnecting the strings and modules to be tested, unlike TIR imaging, which is conducted while the modules are operational. And TIR imaging is a quick method and a non-destructive method. But TIR imaging is generally misinterpreted because of the dynamic nature of operational conditions. So these are the conditions under which TIR imaging should ideally be conducted. That is low wind speed, irradiance of more than 700 watts per square meter, under clear sky, and good capturing angle. So this picture is showing that the reds must be avoided because they cause reflections on images, but the greens good capturing angles. But when TIR imaging is conducted under different operational conditions, the TIR images can be different. Hence, it is important to understand the behavior of thermal signatures under dynamic operational conditions. Okay, so this slide is showing that cracked cells also cause thermal signatures, as can be seen on this TIR image. And the hot cells actually they underperform, and they cause, or they resulted in the module IV curve not matching to the expected IV curve, and no optical impediment or any visual anomaly was seen on this image. So these cracked cells and dark cells, they caused underperformance on the module. Okay, so when conducting TIR imaging, the modules have to be inclined so that they capture maximum irradiance. So this polycrystalline PV module was inclined for TIR imaging and IV measurements when partial soiling was applied on cells in different substrings sequentially as seen in this picture. TIR images of and IV measurements were also taken on a monocrystalline PV module that was operating under varying load. And EL imaging of the modules was taken using the MBGA mobile lab. And the testing techniques were also applied on a monocrystalline array that was operating under varying irradiance and output power. And the next slides I will show the TIR images that were captured under different operational conditions. Okay, so these are the TIR images that were captured under different soiling conditions. And the image of an soiled module is hotspots in a patchwork pattern in substrings 1, 2, and 3. And when partial soiling was applied on a good cell in substring 1, the shaded cell become abnormally hot, and the rest of the hot cells in the substring disappeared and operated as good cells. This dynamic operation of the thermal signatures is also observed after partial soiling substrings 2 and substring 3. So partial soiling on PV cells minimize current mismatch in the substrings, resulting in the bad cells operating and appearing as good cells on the TIR image. And these regions of interest were created and analyzed in Flare Research Studio. And the next slide shows how the operational temperature fluctuates when soiling was applied on the cells. Okay, so these graphs are indicating the dynamics of operational temperature of the regions with bed cells, that is region 1, and regions with good cells, that is region 2. So we can see that line profiles 1A and 2A indicate the temperature across the peak cells of region 1 when the module was unsoiled, with the line profile 1A showing fluctuations in operational temperature due to bed cells in region 1. So when the 3 cells were soiled, the temperature of cells in region 1, as indicated by the line profile 1D, that is in blue line, is almost the same as the temperature of good cells in line profile 2A. So we can see that this yellow line representing the temperature of good cells in region 2 is now almost at the same temperature as the bed cells, which are now operating as good cells, showing their temperature on this line 1D. Okay, so this is showing the shift of MPP when partial soiling was applied on the cells. So the shift of the MPP was due to substrings and was due to the shaded substrings. And as we can see here, the IV curve, when one soil was shaded, is a bump indicating an active bypass diode across the substring. And when more cells were shaded, we have the bypass diode, we have more bypass diode conducting, and the bump shifting towards ISC. And when the cells were partially soiled uniformly, it caused a reduction in ISC, as you can see on the blue IV curve. But that blue IV curve is showing no bump because the shaded substrings were generating equal currents, so there is no mismatch in the substrings, and there is no bypass diode that was conducting when all the three cells in different substrings were soiled. Okay, the table is showing the performance parameters of the module under different soiling conditions, and it can be seen that as more cells were shaded, the current generated by the module reduced, and also there is a decrease in the generated power. Okay, the EL image of the module shows dark cells and cracked cells, which correspond to hot cells. The damaged cells operated and appeared as good cells, as shown on previous thermal infrared images that were captured when the substrings were soiled. So incorporating EL imaging can give detailed information on the state of the individual cells. So on visual image, as can be seen here, nothing was observed to be abnormal, but this image or this picture is just summarizing the cell anomalies that were observed when EL imaging was conducted. Okay, dynamics of the thermal signatures is also seen on these TIR images of a monocrystalline array. The hot cells can be seen on the TIR image that was captured without soiling, and after partial soiling one cell, the hot cells disappeared, and they operated all as good cells due to change in current mismatch in the shaded substring. So partial soiling can mislead decisions to only cleaning the affected modules, yet other anomalies are hidden. Okay, these images and IV curves are of a monocrystalline module that was operating under varying load. And as can be seen, the increase in load forced the hot cells to appear as good cells due to decrease in current produced by the module. And under open circuit conditions, as shown in this TIR image, the cells are warm since no photovoltaic action is occurring, but the incident radiation is heating up the cell. And on the IV curves, we can see that the IV curve of the module has got a bump indicating that the bypass diode across the underperforming substring is conducting. The IV curves of the substrings show that substring 2 is underperforming, and the bypass diode across it is trying to lessen the heating effect of bad cells. Okay, this is showing a decrease in operational temperature of bed cells due to decrease in current when load was increased. Okay, this slide is showing that EL image of the module is critically damaged cell, and other cells with minor and minor cracks. And the critically damaged cell is still showing its abnormal thermal signature at high load. So the cell area affected matters for a significant mismatch to occur, and the area affected can actually be proportional to the operational temperature of the defective cell. Okay, this slide is showing the TIR images of a monocrystalline array that was operating under different irradiance and output power. It can be seen that there are many hot cells on TIR image captured under high irradiance and high output power, and as the irradiance and output power drops, the number of hot cells decrease, as can be seen in these two images that were captured under lower irradiance and lower output power. When the array was off, when it was switched off, the substring with hot cells was actually generating current, which was circulating through the faulty bypass diode, and forced the bypass diode to be hot as it was conducting the substring current when this array was switched off. Okay, the EL image of the array shows that the substring with hot cells is dark. That's indicating that it has a faulty or a shorted bypass diode. That is why the IV curves of the underperforming module and the underperforming strings of the underperforming string have no bumps in it, because the bypass diode across the underperforming substring was defective, and it was shorted. Okay, so as we can see in the EL image, there are some EL features shown on the EL image on those cells, but no abnormal thermal signature is seen on the TIR image due to these EL features. There should be a significant current mismatch for cell anomalies to cause thermal signatures on operational PV modules. Okay, this is showing the shift in MPP due to underperforming substring, and actually it caused a decrease in VOC of about 12 volts when comparing the underperforming substring with the good performing ones, and also when comparing the underperforming module with the other good performing modules. And also about 18% drop in power was realized on a module level, while on a string level about 9% power loss was realized, as can be seen in this table, which is showing the performance parameters of the modules and strings in the array. Okay, so to conclude this talk, TIR imaging quickly provides valuable information with regard to the exact location of an underperforming cell in an operating PV module. And dynamic operational conditions can influence abnormal thermal signatures and affect the results of the TIR image of the affected PV modules. This can mislead decision making during maintenance of PV modules, since some anomalies cannot be reviewed under certain operational conditions. So further insight of failures in PV modules can be acquired by incorporating other inspection methods such as EL imaging and IV measurements. And the other testing techniques are actually necessary for informed decision making. Accumulation of knowledge regarding the dynamic thermal infrared imaging on operational PV modules can improve and develop PV plans, inspections for long-term reliability and hence an improved return on investment of the PV modules. Okay, I would like to acknowledge the Nelson Mandela University, DSI, PV Insight, and PV Research Group, and also ESCOM for providing the necessary facilities and financial aid for this study to be carried out. Okay, I thank you.
Right, thank you, Monphias. Yeah, there's a few questions that's coming our way. So maybe I should just look at the first one. Maybe not exactly to do with cracked cells and thermal imaging as such, but it's an interesting question nevertheless. The listener asks, the loss of energy through heat seems to be a big factor affecting efficiency of silicone cells. Hypothetically, what would be the pros and cons of an actively cooling the module? What would you say, Monphias? Do you think it's worthwhile cooling the module?
Cooling the module, I don't know what the listener is asking. Maybe cooling how actually?
I think, yeah,
because
what it probably means that there's a lot of energy loss through heat, and by cooling the module, you might gain that loss of energy. You know, maybe in the that you're getting water heated, and that you also the module is operating at a lower temperature. So I think he's asking, what effect it has.
So cooling so that the hot cells can operate at a lower temperature.
Yeah, the module. Mm-hmm.
Okay, the module can operate at a lower temperature. Okay, yeah, actually cooling, it depends on how cooling is applied on PV modules. But obviously, if a module is operating at a very high temperature, obviously it will affect the VOC of the module, and also it will affect the operational temperature of the cells. And again, cooling maybe by wind blowing on the modules can also again affect the uniform temperature distribution, because it depends with the wind direction, as it can cause the other side of the module to be operating at a higher temperature than the other cooled side. Yeah.
Okay.
I think
that's more or less answers it. If you look at the VOC of the module, if you look at the IV curve, if you look at the VOC, if your voltage reduces, the amount of power that the module can produce is lowered. So by actively cooling, meaning pumping water or something like that, or blowing air over it actively, will definitely increase the power produced. Unfortunately, the amount of energy that you're going to gain doesn't really offset the cost of pumping water, and the amount of heat that you get from the module in terms of heating the water is also very minimal. So it's been tried many times. There's bladders that they put at the back of the module, and yeah, all kinds of schemes. Not really been successful so far. Another question, Monphias. What are the limitations to thermal infrared imaging? What defects can't be detected? I think you touched on it last few slides.
Yeah, maybe if I can maybe scroll back. Okay, so like I said, as we can see here, we have cracked cells that are showing here as hot spots or hot cells. So like I said, the area of the cell that is affected, it actually cause, or it actually influence the operational temperature of the affected cell. So actually it all depends with the mismatch between the good and the bad cells. If there is a significant current mismatch between good and bad cells, obviously the bad cells is going to appear as a hot cell in an operational PV module. But if any defect or any anomaly on a cell is not causing a significant current mismatch, then that cell will not appear as a hot cell on TIR imaging. So TIR imaging can reveal hot cells of defective cells under certain operational conditions, which cause a significant current mismatch between between bad cells and good cells.
Okay, that's an excellent answer, excellent question. So, so the user needs to be very aware of this, that the thermal infrared imaging is not the last or the best way to look for cracked cells. All it tells you is if there's hot cells. I think that's a very good slide showing that if there's a lot of mismatch when the module is in short circuit, then you will see more mismatch and possibly cracked cells. Again, what Monphias also said earlier is that the hot cells does not necessarily mean cracked. It could be other defects that could also show up there. Thank you. Another question, Monphias, slide 9 shows a damaged backsheet. What do you think is the cause of that? What would the thermal image look like, assuming the cell is still operational? I think it was slide 9.
Okay, slide 9. Okay.
Yeah.
This damaged backsheet.
Yeah.
Okay. This damaged backsheet, obviously, this caused by these are benchmarks which are caused because of a cell that is underperforming, and as you can see, they are running on the bus bars. So it means there is connections failures, that is between the fingers and bus bars. maybe due to faulty solderings. So this can cause resistive heating on a cell, and the cell can appear hotter than the other cells. If I can also show you, okay, on this image, this is more or less the effect of broken or broken bus bars and fingers, which are causing resistive heating. So these burn marks, obviously, they were caused by hot spots due to resistive heating on bus bars and fingers. I don't know if I have answered correctly.
Yeah, that's a good answer. Yeah, I think also good to remind our listeners that one must remember that a photovoltaic module has got encapsulant, polymer encapsulants. Encapsulants means that underneath the glass there are some polymers surrounding the cell, and as we know, polymers are flammable. So if the temperature is high enough to reach the flash point of the polymer, it will catch fire, and it can cause a lot of damage to the surrounding area. So one must be aware of that all the time. I don't see any more questions from our listeners. I might have a few questions that I could ask, but I think we're running out of time. So I'm going to rather ask you privately. So I think we can end off this webinar session. And I'd like to thank everybody again for listening in, and I'd like to thank Monphias for giving us this presentation. And I think the important thing that these rings home is that it's not so obvious. It's not just a case of pointing a thermal camera at a module. It depends very much what the operational conditions are, and the thermal image will change depending on a whole lot of factors. So one can't just take one thermal image and think that is going to be your answer. So thank you very much, Monphias, and also again to thank our sponsors, Eskom, and obviously PV Insight, Nelson Mandela University, the Department of Science and Innovation, and the Photovoltaics Research Group, of which we are all part of. Thank you very much, and have a good afternoon.